In this video, we will start our journey down studying the electric force. Many years ago in Greece, they realized that if you took certain materials like amber and you rubbed them, that you could then reach over and use that to magically appear to pick up various pieces of small stuff. For instance, you could do that today if you rub something like, for instance, silk on a glass rod. You can reach it over and almost as if magic pick up pieces of paper. Well, that meant something about it had a property that had changed, and today we know that the fact that it's able to grab onto the paper means that it applies a force, a new force. You can see something similar if you were to take, for instance, let's say a wall here, and you had a balloon or just a rubber object of some sort, but a balloon is common in these little demos. And if you didn't do anything dumb, the balloon, you just let it go, and it doesn't have helium, just has regular air, the balloon will fall. And that's because we say that the balloon is uncharged, and it's because of gravity that it falls. But what's neat is if you take the balloon and you rub it with a silk cloth or rabbit's fur, or until I lost my hair, I used to use it to rub on my hair to do it. And then if you take that balloon and you stick it near the wall, you'll find, surprisingly, that the balloon sticks to the wall. So the balloon sticks after rubbing with fur. Now that means that we know gravity is pulling down like this. So that means there must be some force now holding it up. And it's not friction, because before we rubbed it, when we stuck it up there, it didn't have anything. And in fact, we have no normal force, it would appear, in this problem. But somehow there is a new force, some sort of force that's entered in the problem. The cause of this new force is what we call charge. So charge is the source of this new electric force that we're going to study, in the same way that mass is the source of gravity. We found through a lot of hard work that there are two types of charge. There is what we call positive charge and negative charge. And whether we called one positive or the other one negative was somewhat arbitrary. They just found that when they rubbed glass with fur versus, say, for instance, another type of material like rubber with fur, that it responded differently. If you took two rubber objects and rubbed them and you put them, they would repel each other. But if you took a glass and a rubber, they would attract. If you took two glasses and rubbed them, they would repel. So they decided to call one of those positive and one of those negative. This was really Benjamin Franklin that was involved, although he didn't call it plus and minus at the time. But because of his conventions, which became positive and which became negative entered into our vocabulary. And it just so happens in a lot of metals, the thing that moves are negative charges. Yet physicists still talk about the movement of positive charges. So two types, positive and negative. Charge is conserved. This is an extremely important fact. You can neither create nor destroy charge, ever. So you may only transfer charge. Many machines are designed to do exactly that, but you cannot say that you created charge. You can only transfer it. So for instance, if you have an object, say one object, and it had 6 units of charge over here, let's say plus 6, and another object over here had plus 2 units of charge, and you were to take and move 1 unit of charge. Then when you were done, this one would have 7 and this one would have 1. The total can never be different. Now, it turns out we believe that probably the total in the universe is 0. Alright? It certainly is pretty much 0 locally. So when you create a positive charge, there is always a negative charge. And I shouldn't really say create. When there is a positive charge on one side, there is always a negative charge. You can neither create nor actually destroy charge. I have to be somewhat careful about this statement. Certainly particles can come into existence from energy we find out in high energy physics. But the net charge is conserved. So if you have a positive particle, you also have a negative. It's as if you split that charge out of a vacuum. The unit of charge in the System International is called the coulomb. It turns out because of the difficulties of actually measuring coulombs, it's not the fundamental unit. The fundamental unit that we will deal with is actually for current, called the amp. And an amp times a second leads to a coulomb. The symbol for the coulomb is big C, and it's named after Charles Augustus Coulomb, who developed Coulomb's law. The charge, we found out, is also quantized. It doesn't just come in any value. It comes in small units. And those units are the unit of E, which is an extremely small number of 1.6 times 10 to the minus 19 coulombs. This is the charge on a proton or on an electron. Something else we've discovered. In many materials, charge is free to move. These materials are called conductors. Now, it was great difficulty for us to figure out why they were able to do this. And in fact, this is somewhat moving towards something maybe you saw in chemistry, but certainly beyond what we would call classical physics. In materials, we find out that there are energy levels that electrons can exist in. This one here, for instance, and there might be a second one up here. And in between this, there is a gap. So you can think of this as a highway, and this is the second highway that the electrons are free to move. But what's interesting is that like all highways, they can get filled. And so this guy here is a filled band. In chemistry, you may have talked about filled shells. That's for a single atom. Many shells go together by interaction to create what are called bands. And if all of these guys have filled this up, there's no way the electrons can move. But in conductors, it turns out that they have electrons up to the next band. And it's filled part of the band, but not all of it. And so it has an empty part. This is called the conduction band. So a little electron, let's say right here, can gain just a little bit of energy, for instance by heat or by light, get up into an open space, and he can pass all the other little electron cars in the material. And therefore, with just a little bit of energy, it is easy to make these electrons move. These are known as type 1 conductors, and examples of those are most of your metals. So certainly copper. Now there are other materials that you would not think in chemistry that they would be conductors, but turn out to be conductors as well. These are materials called type 2 conductors. And in a type 2 conductor, they have a band here, and that band is filled. This is usually called the valence band. So you would think that since that's the end of all their electrons, that they would not be able to conduct. But what's different is they don't have this energy gap, this forbidden region where electrons can't exist. These electrons have a lot of energy to jump up. I might say that's a large energy gap. Think of it as a giant river they have to jump. But there's these electrons that find it very easy to move. Over here, this is the end of all the electrons this object has. But what's interesting about this is that its next band overlaps. So this is an empty conduction band with no energy gap. So what can happen here is that a little electron here can just move along because there are empty states in this overlaying highway, if you would. These two highways have merged, and the blue spaces are empty. So it takes almost no energy for this to go up. Now it turns out it's not quite as easy to jump into this new band as it was in this old band. So these guys are not quite as easy to conduct. These are usually things like magnesium. Things that are closer to your alkaline earth that you might actually think would not be conductors, like is copper, but in fact conduct pretty well. Now some materials do not allow charge to move hardly at all. I should say cannot move. Maybe the better word would be difficult. If a material doesn't, it is called an insulator. And the reason this is that these materials have a conduction band that's very far removed and a field band, a field valence band. And this being a large energy gap. So there are no electrons up here because this is empty. Now, if this gap is not too big, then some of these guys might be able to get enough energy from heat and such and hop up here. As you move this closer, the probability of that occurring goes up. And you get what we call a semiconductor. It's somewhere between an insulator and a conductor. In fact, today in Dallas at Texas Instruments and in Austin, Texas companies figure out by mixing materials how to modify this gap to anything they want. This is the great advantage of our modern electronics. We'll talk more about charge and the other properties in the next video.